This video is our first introduction to differential equations in Calculus 1. Now, a lot of people are intimidated by differential equations. Many of my differential equations students who are taking differential equations after they've taken Calculus 3 are intimidated by it. They don't even know what it means, but they know it's supposed to be hard. It's really not as bad as it seems. If you know how to take derivatives and you understand what an antiderivative is, you understand the idea of solving a differential equation. So here's just something for contrast. In algebra class, we often posed problems like this. We said, here's x squared plus 2x plus 1, and that's equal to 0. And your goal is to find x. Find a value of x that makes this equation true. Now, differential equations is very similar, but instead of having an equation that has an unknown x in it, a differential equation is an equation that involves the derivative of an unknown function. So let me write that down before I give you an example. So it's an equation containing the derivative of an unknown function Your goal when you're solving a differential equation is just to find the unknown function. So here's an example. Let's say someone gives you y prime equals, let's just say y to start. Your goal is to find a function y of x or y of t that satisfies this equation. So you're asking yourself, okay, what function can I take the derivative of that will give me the exact same function back? And if you answered e to the x, you're right, that's one of the solutions to this differential equation. Because what's the derivative of e to the x? It's e to the x. But it turns out there's actually a family of solutions to the differential equation. If I take the derivative of a constant times e to the x for any constant, no matter what that constant is, the derivative of a constant times e to the x is going to give me a constant times e to the x back. So the solution of this differential equation is this function. So over here, you're just trying to find x. The x value that solves this is x equals -1. We typically solve by factoring. We might take the square root, or we could set the factors equal to 0. You could also use the quadratic formula there. We have lots of different methods for solving this equation, but our goal is to find x. X turns out to be -1. Here, the goal is to find y of x, or the function whose derivative is shown in the differential equation. So it's not really that bad. I think the reason why people are so intimidated by differential equations is that the processes that we have to go through in order to find y of x often involve taking derivatives and taking antiderivatives. But if you know how to take a derivative and you know how to take an antiderivative, solving differential equations is pretty easy. You're going to follow a series of steps like you did in algebra. And that series of steps, it all follows will all follow logically from the step before it. So you're just getting closer and closer to your answer in this class through a series of steps that involves a lot of calculus and some algebra. So differential equations, actually the techniques we study for solving differential equations tend to be very, I want to say algorithmic, maybe I'm using the term incorrectly, but it's just following a series of steps to find y of x, just like you followed a series of steps to solve this equation when you were in algebra class. But we're in Calculus 1. Now that you know how to take an antiderivative, you can solve simple differential equations. Now you can't solve this one, not without just guessing, but if this function on the right-hand side were a function of x, you could easily solve that differential equation. So here is a simple differential equation. Now, simple is my term. That's not a standard term in the literature or anything. But let's say somebody says y prime is equal to f of x. What does y have to be? Well, if this is a function of x, and I have the derivative of y right here, in order to get rid of the derivative, I just take the antiderivative. The antiderivative of the derivative with respect to x is just the original function plus c. So I'll just call that y of x. And I don't need the plus c over here because this side's going to take care of the plus c. So this is a very simple differential equation that we can solve now that we know how to take some antiderivatives. So a differential equation is just an equation containing the derivative of an unknown function. In order to find that function, you basically have to undo all that differentiation. If this function on the right-hand side is a function of your independent variable only, so there are only x's over here or t's or whatever your independent variable is, it's just that variable and not this variable, the dependent variable, then you can just take antiderivatives to get the function back. Let's look at a very simple example. Say I have y prime equals 5x squared minus 2x plus 1. Well, y would then have to be the antiderivative of the derivative with respect to x. So that's the antiderivative of 5x squared minus 2x plus 1. So I bring the 5 down, and then I use my antidifferentiation rules to evaluate this. So I add 1 to the exponent, and I divide by the new exponent. Then I bring the negative 2 down. Then I have an x to the first there. So I add 1 to the exponent, and I divide by the new exponent. The antiderivative of 1 with respect to x is just that 1 times x, and then we add c. The 2's reduce, and we get this family of solutions to the differential equation. I'm calling it a family of solutions and not just one solution because of that arbitrary constant. All of these functions, no matter what c is, they have the same slope. The slope of this function is given by this function. For a particular value of x, this is going to give me the slope of this guy over here. This is called a family of solutions to the differential equation. Now this also happens to be the general solution. Or let's just say a general solution to the differential equation. Now, a general solution of the differential equation is the one solution to rule them all. It's the solution that it contains all possible solutions of the differential equation. Now, when we look at nonlinear differential equations in the differential equations class, you'll be able to find families of solution often for some nonlinear equations, but those families of solutions are not necessarily the general solution. There might be some other solutions out there that aren't a member of the family. Those are called singular solutions. Think of them as a black sheep. They're outcasts. They're not in the family. So let me finish writing my sentence. A general solutions is a family of solutions that contains all possible solutions of the differential equation, or I guess to the differential equation. Okay. So that's it. A differential equation is an equation containing the derivative of an unknown function, your goal is to find that unknown function. A family of solutions is a solution containing an arbitrary constant. Remember that arbitrary constant just means it's that graph shifted up and down C units. If C is positive, we're going to shift up C units. If C is a negative number, we're shifting down absolute value of C units. So these are a whole bunch of graphs, infinitely many functions, and all of them have this as their derivative. And if you have a solution that contains all possible solutions to the differential equation, that's called the general solution. I abbreviate that with GS. This is the general solution of this differential equation. If there's a function out there that you can take the derivative of that gives you that original function back, it has to be a member of this family. Every function that satisfies this is a member of this family. There are no solutions to this equation that are not in the family. But every solution in the family works. Y equals 5e to the x works. Y equals 10 e to the x works. Y equals 1/100th times e to the x works. All of these guys work. So that's called the general solution. It's the solution that contains all possible solutions. There are no other solutions out there to this differential equation. And it turns out with this guy, there are no other solutions out there to this differential equation. All the solutions to this differential equation belong to this family of solutions. If I take the derivative of this, I get this. And the only way to get this as my derivative is to be a member of this family. Okay, now sometimes we're given enough information to find the value of this arbitrary constant. As you can imagine, that's very important. Differential equations are one of the most important applications of the calculus that you've been studying in Calculus 1 and that you will study in Calculus 2 and Calculus 3. Differential equations tell us how rates of change of a function are related to independent variable, maybe the function value itself. They tell us it's just a relationship that tells us how that rate of change or the rates of change, second derivative, are related to the original function and also the independent variable. So this comes up in population growth problems, predator-prey systems. I'm sure you guys have watched that video I sent you about COVID-19. That satisfies what's called a logistic growth differential equation. So a logistic model, which is a solution to a certain type of differential equation. So these are really important. We often know the relationship between something's rate of change and the original function and the independent variables involved. But we may not know the original function, and our goal is to find the original function. Differential equations is about finding that function. But in this class, we're going to start really simple. If I know the derivative and I want the function back, I just take the antiderivative. Okay, so sorry, I got off on a tangent. So back to this particular solution and initial condition. Sometimes you have enough information to be able to find that constant. In that case, what somebody is posing for you is not a differential equation. They're not asking you to solve a differential equation. They're asking you to solve what's called an initial value problem. This is a problem consisting of a differential equation and what are called initial conditions. They basically tell you, these initial conditions tell you the value of the function, the value of the function's derivatives at some particular value of the independent variable. They're called initial conditions, or I think they're called initial conditions because that value of the independent variable is often 0, and that independent variable is often t. So they're saying time t equals 0, the velocity is this, and the position is this. So what does the position have to be in general if I know the acceleration? Just for example, but these are values of the function and its derivatives at a particular value of the independent variable. So we know some value of the unknown function, the solution to the differential equation that we're looking for, and its derivatives at a particular value of the independent variable. And the independent variable, that's x. If you have y equals y of x, we're thinking y depends on x. So y is independent, can kind of do its own thing. Y depends on it. Once x does its own thing, y has to sort of follow along. So this is dependent and that's independent. Okay. So that's what an initial value problem is. So let's look at an initial value problem. And then I'll introduce the other terminology listed on the other page. Let's say that somebody tells you that the second derivative of a function is x times negative, or x raised to the negative 3/2. And the first derivative of that function at x equals 4 is equal to 2. And the original function value, at x equals 4 is equal to 0. Okay. Well, if I have the second derivative of my function, and it's a function of x, in order to find the original function, I can antidifferentiate. Notice we've got a differential equation. That's an equation involving derivatives. It's the second derivative of the unknown function. And we've got some conditions. I know that the derivative of the function at x equals 4 is 2. And I know that the original value of the function at x the value of the function at x equals 4 was 0. With those two pieces of information, I can not only find a family of solutions to this differential equation, but I can find a solution to the differential equation that satisfies this and this. These are called the initial conditions, or we might abbreviate them ICs. And this is the differential equation. So we want to find f. Well, first, in order to get rid of that second derivative, I'll take the antiderivative once. The antiderivative of the second derivative is the first derivative. This is already set up, so I can use the power rule. So I add 1 to the exponent. Negative 3/2 plus 1 is negative 3/2 plus 2/2, so that's negative 1/2. And then we divide by the new exponent. Dividing by negative 1/2 is the same as multiplying by the reciprocal, negative 2 over 1. Don't forget your constant of integration. So this is negative 2 over 1 times this. And x to the negative 1/2 can be rewritten this way because of this rule, remember. I can write that as 1 over x to the 1/2. And again, the reason I would do that is because I'm more comfortable with this. I can think about x to the 1/2 and do that in my head, but negative exponents, I don't really think that way. I always sort of convert them and then work here, where the mathematics is a little bit more comfortable for me. So I rewrite that this way, then I multiply straight across, and then I remember x to the m over n is the nth root of x to the m. So this is really a square root of x in the denominator. So f prime is equal to this. So this is a general solution to this differential equation if my goal was just to find f prime. But my goal wasn't to find f prime. My goal is to find f. So if this is f prime, and I want to find f, I need to antidifferentiate again. Since I'm going to do this twice, I'm going to get two constants. I'm going to call that first constant C1. And actually this form, which looks so pretty, is not the best form for computing an antiderivative, so I'll rewrite it again. We've got a -2 times an x to the -1/2. The antiderivative of this comes from bringing the -2 down, then we add 1 to the exponent and divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2 over 1. The antiderivative of constant with respect to x is that constant times x, and then we add a constant of integration. Okay. Now this is a solution of the differential equation. And it's actually a solution to the differential equation that contains all possible solutions of the differential equation. So this is the general solution of the differential equation, f double prime equals x times, or x raised to the -3/2. So if f is equal, or if f double prime equals this, then f must equal this. Now, if I want a member of this family that satisfies these initial conditions, what I'm looking for is what's called a solution to the initial value problem. And the initial value problem is a solution to this differential equation that satisfies this. So the goal is, like, how do I find that solution that satisfies these two guys? Well, with these two conditions, since I have two unknowns down here, I can use those two conditions to find the two unknowns, C1 and C2. So in order to find that, the values of C1 and C2, let's evaluate f at 4 and set it equal to 0. That'll allow us to find one of these constants. So I'm replacing x with 4. So we have f of 4 is -4 times the square root of 4 plus C1 times 4 plus C2. So I get -4 times 2, so that's -8 plus 4C1 plus C2 equals 0. That does not allow me to get either C1 or C2 yet. But I know how C1 and C2 have to be related. 4 times C1 plus C2 minus 8 must be 0. If you're saying, why did you set that equal to 0? It's because of this right here. F of 4 has to be 0. So I find f of 4, I solve, and I see set that equal to 0 because it has to be 0. So this is important. I'm putting a box around it because I'm going to need it later, not because it's the answer. Okay, what else do we know? We also know that f prime of 4 equals 2. And remember what f prime was. F prime was -2 over the square root of x plus C1. I think this is going to be enough to allow me to find C1. So if I evaluate this at x equals 4, I get this. And -2 divided by 2 is -1. So I've got -1 plus C1, and I'm setting that equal to 2. So now I take this equation and I solve for C1 by adding 1 to both sides, and I find out that C1 has to be 3. Okay, so if C1 equals 3, what does that mean? That means that f prime of x is equal to 2 over square root of x plus 3. And if I know that C1 equals 3, I can substitute that in over here and get C2. Okay. So I've got -8 plus 4 times C1, which is 3, plus C2 equals 0. So -4 plus, I keep saying -4, -8 plus 12 is 4. 4 plus C2 is 0. So C2 equals -4. Okay, now you're not done solving the differential equation. You're not done solving the initial value problem until you've stated a function that has this as its second derivative and also has this and this and also satisfies this condition and this condition. So the final solution to the initial value problem is this function, but I replace C1 with 3, and I replace C2 with -4. So f of x is -4 times the square root of x plus C1 times x. C1 is 3, and C2 is -4. Now you should check, if I evaluate this at 4, I better get 0. And if I evaluate the derivative of that function at 4, I better get 2. So let's check our work. F of 4 is -4 times the square root of 4 plus 3 times 4 minus 4. So we get -8 plus 12 minus 4, which is 0. Good. And then we could rewrite it this way. Take the derivative. So we have -4 times 1/2 times x to the -1/2. Derivative of a constant times x is just a constant. Derivative of the 4 is is 0. So I've got f prime is equal to -2 times x to the -1/2 plus 3. Evaluate that at 4. So I've got -2 over 2, which is -1. -1 plus 3 is 2. Is that my initial condition? Yes. Okay. Now, I haven't finished checking yet. All I found was that f of 4 equals 0 and f prime of 4 equals 2. I guess the last thing I need to do to make sure that this is the solution to my differential equation is take the second derivative. If I take the second derivative, I better get that back. If I get that back, then I know I've solved the differential equation. So let's take the derivative of this piece. So I have -2 times, bring the -1/2 down, multiply by x to the 1 less power. Derivative of 3 is 0. And that simplifies to a 1 times x to the -3/2. Okay, so I've got a function that satisfies both initial conditions and satisfies the differential equation. Now, here's some new terminology. This function here that satisfies the differential equation and both initial conditions is called a particular solution to the differential equation. A particular solution of the differential equation is a solution that does not have any arbitrary constants in it. Now, we can find particular solutions of differential equations by finding general solutions or families of solutions and then finding the values of the constants like we just did. We can also find particular solutions of a differential equation just by guessing, like this one. Y prime equals 3y. We don't know how to solve that yet. You'll learn how to solve this when you take the differential equations class. But if I'm looking for a function, y, as a function of x, that satisfies this, I'm looking for a function when I take its derivative, I get the function back, but I get the function back times 3. E to the 3x will work. That is a particular solution to this differential equation because it doesn't contain any constants. It happens to be a member of a family of solutions. This is a family of solutions to the differential equation. And this family turns out to be the family of solutions that contains all possible solutions to this. So this is a family of solutions that is also the general solution of the differential equation. Again, if this differential equation is what's called nonlinear, which we'll define in the differential equations class, you might have a family of solutions that doesn't contain all of the solutions. So we would just call that a family of solutions. When this differential equation is linear, when things are nice and everything's well behaved, we often can find this family of solutions that contains them all. Like this was a family of solutions that contained all of the solutions of the differential equation. Okay, so we defined a particular solution. That's a solution without any arbitrary constants in it. We talked about initial conditions. Those are values of the function and the function's derivatives at a particular value of the independent variable. Or if the independent variable is x, that's a particular value of x. And a general solution is a family of solutions that contains all solutions to the differential equation. And the differential equation is just an equation with a derivative in it. You're trying to find the original function. Let's do one more example. Excuse me. Let's say that somebody tells you that y prime is equal to let's say x cubed times 2 over x squared minus 1 over 5x to the fourth, and f of 1, or excuse me, y of 1 is equal to 4. So this is an initial value problem. I'm given a differential equation, and I'm given the initial value of my function. This initial value problem, I often abbreviate IVP. Consists of a differential equation and an initial condition or initial conditions. Usually you get one initial condition for every derivative over here. So if you have a first derivative, you're going to get one initial condition. If it was second derivative, like on the last one, you get 2 initial conditions. Okay, and notice that this is a function of x. Since this is a function of x, if I want to find y, and I know its derivative, I just take the antiderivative. The antiderivative of the derivative will give me the function back. And this will produce what's called a general solution. We're going to have a constant of integration. And this initial condition will allow us to find the value of that constant. Now, I don't have a product rule for antiderivatives, not yet. So we've got to simplify this. One way that I would simplify this is to just distribute the x cubed. You can think of that as an x cubed over 1 if you prefer. If you multiply straight across, you get 2x cubed over x squared. Over here, we're going to have x cubed over 5x to the fourth. Now with each of these, I want to pull out any constants. And there's an implied 1 in that denominator and an implied 1 in that numerator. So the constant here is 2 over 1, so just 2. And then if I've got x to some power over x to a different power, remember from algebra class, we just subtract those exponents. Over here, don't pull out a 5, it's a 1 over 5 because that 5 is in the denominator. If I subtract the exponents, I get x cubed over x to the fourth. I subtract 3 minus 4 is negative 1. Now careful here. We can use the power rule for this, but remember we cannot use the power rule if you have a negative 1 as an exponent. If you have a negative 1 as an exponent, you want to rewrite it using this rule. Saying, what do you mean? Well, I want to write that as 1 over x to the first power. And then I see that looks much better. That looks like a rule that I have in my table, the antiderivative of 1 over x is natural log of the absolute value of x. Okay, so I'm taking the antiderivative term by term now. After I've distributed and simplified, I finally got here to a point where I've got a rule for that and a rule for that. Then I bring my constant down, add 1 to the exponent, and divide by the new exponent. Over here, bring the constant down. Antiderivative of 1 over x is natural log of the absolute value of x. Don't forget your constant of integration. So this is why, if someone just asked me to solve the differential equation, I would stop here. I'd say y equals x squared minus 1/5 natural log of the absolute value of x plus c. That's the general solution. But they didn't ask me for a general solution. They asked me for a solution to an initial value problem. So I want to use this initial condition to find the value of c. They're telling me that when x equals 1, y equals 4. So I can evaluate this at x equals 1. Y of 1 is this. And remember, natural log of 1 is 0 because e to the 0 power is 1. And I end up with 1 plus c. They told me that y of 1 was equal to 4. So we set this equal to 4 and we solve for c. Well, if 1 plus c equals 4, then c equals 4 minus 1, which is equal to 3. We're not done yet. A lot of people just stop there and they say, what? I'm done. You didn't solve the initial value problem yet. You haven't solved it until you've stated the particular solution. The particular solution to the initial value problem, or to the differential equation, which happens to be the solution to the initial value problem, is this function, but you replace c with 3. If I take the derivative of this, I get this, and I can show through algebraic manipulation that this is equal to that over here. And if I evaluate this at x equals 1, I get 1 minus 0 plus 3. So I get 1 plus 3, which is 4. And y of 1 was supposed to be 4. So that's the solution to the initial value problem. Now there's one more thing I want to show you. Let's look at an application problem. Now, if S of t represents position at time t, then its first derivative, that's the instantaneous change in position with respect to time, is the velocity at time t. And the acceleration is the second derivative of the positions, the rate of change of the rate of change. Now, if someone gives me acceleration and I want to get velocity back, well, I just have to anti-differentiate. And if I have velocity and I want position, I have to anti-differentiate again. Now, every time we anti-differentiate, we're going to have these arbitrary constants in our solution. We never want arbitrary constants in a position function or a velocity function. We'd like to know what the position actually is at a given time, and having an arbitrary constant in it really doesn't tell us much. So we need some initial conditions here. If somebody gives you acceleration, I would need to know what the velocity is at a certain time and what the position is at the same time in order to find the position function without any arbitrary constants in it. If I'm given velocity, so it's the first derivative, I need a condition on the original function to find the position as a function of time without any arbitrary constants in it. But the idea is this: we differentiate to go this way. If you want to go this way, you have to anti-differentiate. And then use initial conditions to find the values of the constants. And those constants are called constants of integration. Okay, so let's look at an example. This is just one example. There are lots of examples involving instantaneous rates of change. You're going to see a lot more of those when you take the differential equations class. Okay. So let's say this is our problem statement. A baseball is thrown upward from a height of 2 meters with an initial velocity of 10 meters per second. Determine the baseball's maximum height. Okay, and they haven't told us this here, but acceleration due to gravity on Earth is approximately negative 9.8 meters per second squared. Okay, so we know acceleration as a function of time is negative 9.81 meters per second squared. If we want to get the position function from this, well, I need to antidifferentiate twice because acceleration is the second derivative of position. Well, let's just go one step at a time. Let's go from acceleration to velocity. Velocity is the antiderivative of acceleration. This is the antiderivative of negative 9.8 with respect to time. Now I know we're using t instead of x, but it's just a dummy variable. It just tells you that's the variable we're integrating with respect to, but the rules are going to be the same. If that was an x, I'd use an x. If it was a y, I'd use a y. If that was a u, I'd use a u. It doesn't matter. The rules from before, in the rules that we stated before, all of those x's could be replaced by different letters, and it's just a placeholder. And all of that, replacing that x with a different letter would be completely okay. And that's kind of what we're doing here. We're saying, what's the antiderivative of negative 9.8 with respect to time, or with respect to t? The antiderivative of a constant is that constant times t plus a constant of integration. We call that C1. Now, at this point, I could antidifferentiate again to get position, but I know my initial velocity. They told me that somewhere in the problem statement. They said a baseball is thrown upward from a height of 2 meters, watch this, with an initial velocity of 10 meters per second. So we're going to assume time t equals 0, or t equals 0 is the moment when that baseball is thrown upward from a height of 2 meters with this velocity. So with that in mind, we're going to say v of 0. So velocity at time t equals 0 is 10. And if I know v of t is this in general, and velocity at time t equals 0 is 10, then that will allow me to find c1. So we'll evaluate this at 0. So I get 0 plus c1, and then we set the result equal to 10. So we find out that c1 must be 10, which means our velocity without any arbitrary constants in it must be negative 9.8 times t plus c1, which is 10. So that's our velocity, and that's actually a really good velocity function. Somebody tells me a time now, I can tell you what the velocity of that baseball is. Okay, if somebody asked me for velocity, I'd be done. But they asked for maximum height. Ooh, maximum height. How are we going to find maximum height? So we'll think about that in a little bit, but I know I need height. So if I want to find height, Well, that means I need the position of this baseball. So here's a person. At time t equals 0, it threw that baseball up with a velocity of 10 meters per second. It was 2 meters off of the ground at that time. And what's going to happen? The baseball is going to go straight up, and then it's going to come straight down. It looks like it's going up like some kind of horizontal displacement. It's not. It's just supposed to go right up and then come right back down. And this is going to describe the velocity. Okay, now we want the height. We're asked about the height, so we want the height. So I want to find position from velocity, or height from velocity, same thing. And then in order to get position from velocity, I take the antiderivative of velocity with respect to time. So we bring our constant down to t to the first. Add 1 to the exponent and divide by the new exponent. The antiderivative of a constant with respect to t is a constant times t. Then we add a constant of integration. I already used c1 for that one, so I'll use c2 for this one. So I get negative 4.9 t squared plus 10t plus c2. Again, problem is I've got height with an arbitrary constant in it. But they told me what my height was at time t equals 0. That's an initial condition. They said it was thrown upward from a height of 2 meters. So at time t equals 0, the height was 2. I've got an initial condition right here, and I've got another initial condition down here. Okay, so I can evaluate this at t equals 0. I get 0 plus c2, which is c2, and I set that equal to 2. So c2 must be 2. So now I've got height. It's negative 4.9 t squared plus 10t plus c2, which we just found was 2. So that's height as a function of time. Now the question says, determine the baseball's maximum height. Well, you've got some options in that. You can say to yourself, well, that's a parabola. Let's look at height as a function of time, height versus time. How can I find that maximum height? Well, I could take the derivative and set it equal to 0. But isn't taking the derivative of this and setting it equal to 0 the same as finding the velocity? That's the derivative of this, and setting that equal to 0. Actually, I think that makes sense. Our initial velocity was 10 meters per second, and gravity's pulling it down. So it's going up, but it's going up slower and slower and slower until it gets to the top, and then it has a 0 velocity. And then that velocity becomes negative and it starts going down, and it goes down faster and faster and faster. So I think it makes sense that to find this critical point, I take the derivative of this, which gives me velocity, set the velocity equal to 0, which means it's not moving. It's that momentary not moving, that moment when it's not moving at the top. And then I'd solve for t. But they didn't ask for t, they asked for the baseball's maximum height. So once I find the t value, where that happens, I need to find the height at that t value. So I'll just substitute that t value into this function. Okay, so let me write down our process. To find the maximum height, I'm just going to call it h max. Set h prime, which happens to be velocity, equal to 0 and solve for t. And I'll call it t max. And we're going to substitute that into this function here to find the maximum value of the height. Okay, so we've got velocity is this. Set that equal to 0. Solve for t. So you have negative 9.8 t equals negative 10. So it's a little bit more than 1 second. So I get about 1.02. Again, if somebody asks you for the maximum height, don't say 1.02 seconds. Doesn't make any sense, right? So we've got to find the height when t is equal to this value. I'm going to write t at the maximum because that's a little bit more precise. It's not t max, it's t at the maximum value of the height. Okay, so we'll evaluate height at that particular t value. That's the maximum height. So that's height at, I think I want to use that other version, 10 over 9.8. So I get negative 4.9 times t squared plus 10 times t plus 2. And I'm substituting in 10 over 9.8. Just a little bit more precise than using that decimal approximation. So I've got negative 4.9 times 10 over 9.8, close parentheses squared, plus 10 times 10 over 9.8, close parentheses, plus 2. Oops, not plus 1, plus 2. I get about 7.1. And let's look at our units. We had height in meters, velocity in meters per second. So that's a maximum height of 7.1 meters. Okay. So this application problem required solving a differential equation. Now they didn't give us this, not here, but above the problem statement they said, use the fact that acceleration due to gravity is negative 9.8 meters per second squared. When I anti-differentiate acceleration, I get velocity. When I anti-differentiate velocity, I get position. If we're talking about vertical position, we often call that height. Now, if somebody just asked me to solve the initial value problem, I'd be done right here, but they didn't ask that. They asked me to determine the value or the ball's maximum height. So I said, okay, I want to maximize this function. It looks like this, which means I want to find the place where the derivative of the height is 0, where the derivative of the position is 0. Well, the derivative of position is velocity. So I set velocity equal to 0, solve for t. I evaluate the height function at that particular value of t, and then I get the maximum height right here. Now there are population growth problems. There are all kinds of problems that involve solving differential equations. This is just one of them. You've got a few more in your homework.